Hello guys, welcome back. So we are still working on our operating system, and today will be the first part of us working on our physical memory manager. So let's get right into it. Right, so here we go. So I guess the first order of business is to make sure that everything still works, and I also want to, since we are going to use it quite a bit, sure, let's do this. I want to make sure that we do have this boot info thing. So boot info. Right, so let's make sure we can build this and see where we go from here. Right, so it builds fine. Let's see if we have QEMU here somewhere. Sure. Right, so we do have a problem here. So we are overwriting an entry. So one of the blocks we load from our elf file is basically not page line. So let's take a look. Let's take a look at what it is. So read elf-a build kernel 64. Right, so let's see here. Text is page aligned. So we have this global offset table here. That's not page aligned. Let's go over to our linker file here. And since we are not specifying it, I might as well just go ahead and do something like this, just to make sure that it works. And let's see here. Okay, so we don't have the warning anymore, but we are not executing anything here, which is a problem. Right, so why might that be? So if I do this, okay, so the issue is on that print. The issue is on this print. So can we do something like this? Of course, spell it first. Okay, so we do have a bit of a problem here. Right, so let's do something like any opaque, just to make sure that we rather this. Okay, and this, the any opaque has the correct pointer value. So it does point to the correct thing. And I guess, right. And so that means that if I go ahead and do just something like boot info, info, like so, can I then do something like this and get it to work? I guess not. Hold on. So what's the error here? External variable cannot have type. Only external structs and ABI sized packets are okay. So it does not like it being a pack struct. Huh. Okay, that's that might be a problem. So let's for now just go ahead and make it an external struct. So packed structs in packed in Zig doesn't have the same semantic value as packed in C. So that's kind of weird, but All right. And since we are using these values, I'm just gonna get rid of all the default values since we are not going to need them. Right. So now we are going to make this an extern struct, which means that we are also going to make this an extern struct. Not necessarily. So the thing that we are going to need to change is that these we are going to be obliged to make them split them into actual ABI sized things. So 248 divided by 8 is 31. So that's 31 U8s, and 192 divided by 8 is 24. So 24 U8s. Okay, so now if I go back here, try to rebuild this, and let's rerun it. Okay, so still same issue. Cool. Well, first of all, I'm just going to fix something that's been bugging me here. So 0 to 12. There we go. And with this should be fine. Okay, so yeah, just something to keep in mind. Right, so here we are printing this as an any. Let's do something else. Let's print bootinfo.magic. Magic. And that's a actually let's print that as a string. Is it though? I don't think it is. It should be. So actually, let's go up here and do 4 U8s. Right, and this one here would be .magic. Yeah, sure. Let's see what we get. Still nothing. Let me just check something. No, it looks fine. Actually, let's do something here. Let's recheck the ELF file. All of them are page aligned. Hold on. So now we don't have the global offset table though. Is that the issue? Hold on one sec. So I'll first of all start by going here, doing this, and just, oops, there we go. Just do this in debug mode. Okay, so in debug mode, we don't get rid of any of the symbols, and it works. And if I go all the way up here, here we can see that we have, right, so we don't have that, but we still have our symbol, our boot info symbol. Right, and if we do the exact same thing, but in release mode, where we strip all the debug symbols, we get this weird issue here. Okay, so let's go back to our linker here, and let's just do something like this, right? Just remove this. And see if this is going to make it any better. So it's not. So we have something working against us. Right. Right. And I'm not sure what that is. So boot info. Right, let me check something first. Boot info.magic. Boot info here. Right, I guess it's time to break out GDB. And go here, do this, run that. Right, so target remote. So we get sources from build. Actually, yeah, we might have an issue with debugging this since we are aggressively stripping the module. Maybe I'd like to get rid of this. Let's see here. Okay, so I guess the stripping of the module caused the issue that we were seeing. Since I don't know why, but my theory is that the boot info definition just got cold, even though we're using it. Right. So with this, we should be fine. It's working okay. So let's take this from here. We don't need it there, and let's create a new file that I'll physical memory.sig. Right. So I guess we are going to need stud import stud that, and we are going to need a few other things. But for now, let's go ahead and make our so const or yeah, sure, const extern. Is it extern const? Extern const boot info of type boot info. So I guess, of course, we are going to need to get this type here. So this one would be import boot info.sig, and from that we get boot info. Right. So here we also want to define a struct that we are going to call physical memory manager. Yeah, sure, why not? This one would be a struct. Let's give it that. And to interact with this struct, we are going to define in this module here a var memory manager of type physical memory manager. Yeah, sure, undefined at the start of this, and then we'll have a public function in it. Does nothing other than maybe is equal to init, and here we are going to probably do const self is at this, and have a public function in it that takes nothing and returns self. So in this, we are going to do something like this. So this is a nice placeholder for us to have. As for the other things we'd like to do in this module here, we'd like to be able to commit pages, uncommit pages, and allocate pages committed or not, and probably free pages. Right, so we'll need 4 functions here to be able to control all of these items here. So first of all, let's go for commit pages. And for here, we need a count, which will be a u64. This will return a void for now. Actually, let's return a boolean. Let's say if we could commit those pages or not. So for now, we are just going to do placeholders. So count goes there. Then we go for pub uncommit pages. Sure. So count of pages to uncommit. And here we don't really have anything to give back, I don't think. And here we allocate pages. So here we'd like to have a number of pages to allocate, and we'd also like to have some arguments, which would be a struct. And this struct here will tell us if the pages are committed already, and it will tell us if we want to zero out those pages. And from this allocation here, we are going to return some sort of range. So basically a range would be a pointer and phys range, let's call it. Sure. So a pointer and a size, basically. So same as actually, now that I think about it, should we not just return a slice? So maybe something like slice of U8s. U8s. I don't know. So count and this args. Right, and public function. So free pages, and here we are going to basically take whatever we return here. We should expect that. So if we return a slice, we should take a slice as input. Is that fair? I think that's fair. So pages. The only issue with slices is that you can create them, you can get them back from other things in the language and library and stuff like that. So I'm not really a big fan of relying on those. So yeah, let's just create our own slice wrapper. So this one is basically call this range. This will be physmem range, and this would just return void. Or so can we error at any point here? Is an error something that we are allowed to have, or does an error cause panic in the kernel? So that's a valid question to ask, I guess. But for now, let's ignore it. That's the best course of action here. Right, so here we'd like to define const physmem range to be a struct, and this struct here will have so a p address, rather a start, which I will define as p address and a length. Sure, let's write it out, which should be a U64. And we are going to define the address to be, so what's a p address? I guess p address is just a U64. Right. And I don't think we need any other information from this. Right. Okay, and let's get back to this. So what do we need here in our physical memory manager? What are the things that we want to keep track of? First of all, we are going to need the memory ranges, all of them. And this would be a memory, a phys memory list. Phys memory range list. Yeah, I'm not the biggest fan of the name, but sure, why not? And from here, we are going to take memory ranges. We'd like to know. In my mind, this represents all the ranges, and it's not something that we are going to use because it's the combination of all usable and unusable ranges. It's the global view of memory. So what I want to do is actually go for 3 ranges, which would be the same thing, range list, maybe get rid of, there we go. And then maybe reserved ranges, so same thing here. And we would like to track uncommitted pages count, which would be a U64, and the committed pages count, which also would be a U64. And maybe before we do these, we'd like to track our free pages count, U64, and our reserved pages count, a U64 also. Right, so here let's go ahead and declare physmem, whatever called that range list. So this one here will be oh, we already have lists, so let's get our lists. So doubly linked list is at import list.zig, I believe. And from this, we are going to get doubly linked lists. Cool. And here we are going to create a doubly linked list for a type T, which would be a physical memory range list item. Okay. Yeah, sure, okay. Let's do something like this, and then we are going to need to declare that physical memory range list item to be a struct with a physical memory range. So range is a physical memory range, and yeah, prev and next. So const self is ds. So this one would be self, rather a pointer to self, a nullable pointer to self, and next would be a optional nullable pointer to self. Yes. Yes. Speaking of lists, so last time I was editing the, so when I was editing the last videos, I've noticed that in the remove here for the double linked lists, I copied the while loop that we did for our single linked lists, and I felt a lot of grief from that, so I went ahead and fixed the implementation now. We don't really need to loop through the list. We have our current pointer, our current node, as given by the parameter here, and from this we can fairly cheaply get our previous and next pointers, and we just link them together. That's my bad. So I also went ahead and created this for a little bit of proof of concept, and the idea here is that I wanted to create a link that had the previous and self, and I wanted to be able to embed it into something else. So if I go here to the test I've created for this proof of concept, I have this test type here. I have my link field here embedded into this test type, and I create a list from the links, basically. And I append links to the list, and then I use this field parent pointer by giving it the field name and the field pointer, we can compute basically our list will be so link 1 from item 1 and link 2 from item 2, etc. But once we have a link, we can then, so we know that link, the field link has an offset of n bytes into its type, which is this type here. And so we can do link field minus the offset to get the parent of that field, which is basically what this magical thing here does. It's a very known trick in C also to get the container of a field from the field itself and its offset. It's a bit of a macro magic in C. And from this, since we have the parent, then we can get the parent and work on that. So this basically lets us embed list items without having to specify next and previous fields on the parent itself. It's just a little bit of fun. Let's get back to what we are doing here. So now that we have everything that we need, I've forgotten something very important, which is since this physical memory manager will be accessed by multiple cores, multiple threads, and multiple processes in our kernel, we are going to need to protect it from concurrent use. So for that, we are going to need a lock, and this lock will be a spin lock, I guess, which we still haven't implemented. So how do we go about this? Right, here's how we are going to go about this. So synchronization.sig and const stud is import stud there, and const spin lock is struct. Sure. Right, so we have the spin lock. We are going to, first of all, let's do the basics here. Now that we have our solve, we are going to also need a function to create it. Init, sure. No, actually, I'm pretty, maybe I call it create. So this one will return a new spin lock return. So now what do we track? What are the ingredients we need for our spin lock? So I guess we are going to need a, it's a fairly complex topic and it's going to need a its own explanation video, but overall spin locks, you will need to know which of the cores is currently locking, or basically has the ownership of whatever the critical section is. So you are going to need, how do we go about this? I guess CPU ID. Let's give that a U64 or maybe U32. And I guess CPU ID also would need to be defined, because how do we give our cores IDs? Sure. And then we are going to need, well, actually, I guess we are going to need to see if we are locked. Let's say Boolean. Depending on the dimension you examine them, there are two types of locks. The locks that are re-entering. So basically, you can, from the same thread, relock the same critical section multiple times. Since you are the same person locking it, you can lock it multiple times, but then you must unlock it the same number of times. And that's what we are going to be using here. So I guess lock count is something that we would like to have. And we are also going to need to save some state. Mainly, I think yeah, let's just save the interrupt state. Saved in state. Right, and this would be just a boolean, just so that we know if interrupts are enabled or not when we take the lock, so that we can reset. Since we don't have, or we don't want to have any interrupts that are going to occur within our critical section, the spin lock upon lock-in will need to disable interrupts, and upon exiting, the spin lock will have to restore the old state. So if the interrupts were already disabled, it will have to leave them disabled. If they were not, it will have to re-enable them. So long story short, we are going to do CPU ID. Yeah, CPU ID. So here I'm going to initialize this with some sort of invalid CPU ID. And I'm guessing I'm going to have to create this here. So invalid CPU ID, this would be stud. We have stud math max int, yes. Right, so U32. 32. And locked would be false, obviously. Lock count, this would need to be 0, of course. And saved in state would need to be, I guess, undefined, but for now, let's put it as false. Yep, sorry about that. There we go. So we are also going to need a public function lock that takes a self does nothing with that. Well, does nothing with that for now. And public function unlock self, and there we go. There's clearly something to be done here with the API we want to expose. But for now, let's just leave it at this. So now let's go up here to spin lock is, so import synchronization.zeg. There we go, that's spin lock. Right. And I guess we can go ahead and initialize these. So lock will be just .create. If you're asking what this syntax is, this is the new Zig syntax as of Zig 14 or 0.14. You can basically just call a function that's in the type by using the shorthand here. So memory ranges would be, so physical memory list. Do we have something here? No, we don't. So we just create that there. Same for, so let's do this. So here free ranges would be that. And actually, forgot something very important here. There we go. And oops, free ranges and reserved ranges gets that too. And then we get free pages count to be 0 and reserved pages count to be 0. And we want the uncommitted pages count to be 0. Actually, let's set everything to zeros and then we'll advise. Right, so that's for our initialization. Right, so here we are going to call init on this just to create this struct here. And then we are going to, so I guess we have a bit of reclaimable memory, or actually, hold on, let's do things first. So memory.log.log. And the fur mem.log.log, just so that we don't forget that. I'm not really a big fan of doing this here. I would rather have some sort of mm.log critical section, something like this, in which I pass a function to be executed, and all the return paths from this function here would basically get correctly unlocked afterward. But yeah, for now, let's just keep this going. So we want to reclaim our freeable memory. Hold on, this is Zig, right? So reclaim freeable memory. There we go. And we want to, I guess, init free init memory init ranges. So basically, I want to just go ahead and mark all the freeable memory as free in the boot info struct here. And then I want to go ahead and create all these ranges here from that struct that we have. And then we are going to come over here and set so free, uncommitted committed pages, or rather I should be doing this. Uncommitted pages count is equal to free pages count, since all free pages for now will be uncommitted. This here will set our free pages count and our reserved pages count, but we'll just do this ourselves. Right. So with this, we can probably go ahead and declare our reclaim freeable memory. Does nothing, returns void. Very good. And let's also declare the other one, because I hate seeing red on my screen. There we go. Right, so let's do a bit of cleanup here. Oops, well, that's not what I wanted to do, but okay. There we go. So we are going to need this, and we want pmem.sig. Okay. Right, so reclaim freeable memory. So first of all, we are going to need to get the memory mappings from bootinfo.sig. So here I'm going to create a const mmap entries. Sure. And this mmap entries here will be of type slice of boot info.mmap entry. And let's mark this as var and give it undefined as its value. I have no idea where I'm going with this, but let's see. Right, so here reclaim freeable memory. Okay, hold on. Let's do things first. So const log is sed log scoped and pmem. Right. Now I think we have all the ingredients. We can get started. Right. So first of all, log.debug, and I want boot info pointer to be the pointer of boot info. Yep. There we go. That's pretty good. Now that we have this, I want so const mmap. So const mmap pointer is boot info.mmap, but we want to cast that. So let's rename this mmaps, give this a type of multi-pointer thingy to boot info.mmap entry, and we're going to cast that. Or since we know the type, I guess we could just go ahead and do a pointer cast like so. Probably need to take the pointer of that. Right, so now that we have this, we are going to need to compute the number of mmap entries that we have. The way we do this is that we know that we have a header size, so boot info header size, and then we have on the boot info itself we have boot info.size, right? And the difference between these two fields is the so basically if I do this, actually the other way around, so header size, this one is the actual mmap size total, and if we divide that by the size of one single mmap, then we get the mmaps count. Right, so that's what we are going to do here. So boot info header size. This would be, so this is going to be int from pointer of mmaps minus int from pointer of boot info. Yes, and we are going to log this debug. So boot info header size. Actually expecting, so I already know we are expecting 96 bytes. Got this number of bytes, and this one here would be boot info header size. Yes. Then, oops, hold on. Then we have basically mmap size. Let's call it mmap size, which would be boot info.size minus boot info header size. Yes. And we are going to also log this thing here. So mmap size is the do that, and then we do mmap size. Oops, there we go. And then here const mmap count. This would be at division exact of, actually let me just add here size of an mmap entry is at size of boot info.mmap entry. And this here would be, well, what we compute there, and here would be a size of a, well, what we just wrote there, mmap entry. There we go. And of course we are going to print that out. So mmap count is the, okay, let's do this, let's do that, mmap count. There we go. And of course here we are going to set mmap entries to be, so mmaps between 0 and mmap count. Does that work? I think that works, but we'll see. Okay, we're building at least. Oh, yeah. there's a slight issue here. So let's go to main and maybe use what we just created. So pmem.init. Sure. And here we are going to create pmem is import pmem.zig and let's go ahead and write all and go back here and build it again. Okay, spinlock is not marked as public. That's actually fine. Sync spinlock public. And I guess we haven't marked this as public either. Oh, that's fine, because we are never going to use it from outside this module. Yep, that's pretty okay. Right. Yes, let's go again. Pointer cast, discuss const qualifier. Sure, brother. Which one was it? This one. Are you happy with this? So expected type of okay, but found okay, const. Right, since we are never going to be modifying these directly, actually we are. We are going to be doing that. So let's go back to everywhere else. And I guess the const modifier is set on this, right? Yes. Okay. So node struct is declared here. Unused argument in what? Oh, okay, I see. I see it. So it's down, and let's go here and maybe use that argument. Okay. Reserved pages count instruct. No field named reserved. Oh, reserved. Reserved. Right. Okay. All right, let's go. Okay. Oh, that's bad. That's really, really bad. That's not what we want. Okay, that's bad. That's problems that we did not need. So how do we go about this? I think since we've moved from back to extern, some of these fields here would see their alignments adjusted, or rather, they would actually use the API's natural alignment instead of just getting packed. And let's see here. So this one is a 4 U8s. It would have a natural alignment of 1 byte. This one is a UA2. It has an alignment of 4, and it should be fine since we are page aligned. So this one would be 1, but we have 4 of them. This one would be 4. This one would be happy. Bootloader type is a U8. So it has an alignment of 1. It should be happy where it is. This one here has an alignment of 1, so it should be okay. So here we have, okay, this one is 4, this one is 4. This one is a U64, it wants an alignment of 8. So its natural alignment is 8. Whereas we have, here we are aligned to 12. So we have 12 bytes before it. So it's aligned to 12. It's not aligned to 8. Right. That's a bit of a very bummer, actually. Okay, so how do we go about this? I guess I could force the alignment here to be 1. But then all of these would need to have their alignments. Hold on, let's think about this. So this one here would be aligned to 12, or rather to 4s. And we'd have 8 bytes there. This one here would be, so we had 12, and now we'd be at 24, I guess, here, which is still 4 aligned, still 4 aligned, still 4 aligned. This one here would be 1, I think. U8, yes, 1 plus 31 is 32, so still correctly aligned. 32 is 8 bytes aligned, so this one here would be fine. And this one here would be fine, and this one here would be also fine, since we have 24, and this one here wants to be aligned to 16. And all of these before are 96, which is basically can be divided by 16. Yep. So I guess with just this here, we could save this. It's not really the best way to go about this, but yeah. Okay. Right. It's not really the best way. The best way would be to go back and align all the fields, or rather pad all the fields correctly so that they can be aligned. So we need here to add 4 bytes of alignment so that we can go from 12 to 16 bytes above this pointer. But this means that we are going to have to do this change in the bootloader's UEFI and BIOS, and not really about that life at this exact moment. So yeah, we move. We just move. Right, so here, let's see. We have 96, expected 96. We get the mmap size is 384. I'm pressing hard X on that. Let's do something here. So boot info size. Right. Yes. Okay. All right. Let's see. So what's our size? We have 528. 528. So 528 minus 96 is 432. But hold on a minute. Why did this just move? Wasn't it something else just before? Uh-oh. Okay, so I guess we are going to need to delve a tiny bit into our boot loader here. So where do we? There we go. Mmap entries. Get mmap entries. This should be there. And mmap key, descriptor size, mmap size. Okay. And we have indices here. That's actually fine. And we increment the indices there. And let's do something here right before we go out. Let's do something like info. Let's do found the mmap entries. Or created, sure. And then let's go all the way up to main. And yeah, sure, somewhere in here. Well, not this main, the UEFI main. No, UEFI main. There we go. And here, right before we exit from that, I would like to log info, boot info size is, yeah, sure, something like this. And this would be boot info dot size. Are we okay here? I think we should be okay. Did we pass it boot info here? Yes. And did we increment the size correctly? Boot info, where is boot info size? Oh, there we go. So we did increase the size. Boot info size is this. Oh, actually, hold on, we created a problem here. So mmap index and boot info.size. Right, and if we go back here, we don't really need to print this here anymore. Okay, let's go again. Right, so we have 25 of those. We have a size of 496, which is correct. All right, so we should be fine. Let me just rerun this again and see. Okay, so there's a slight variation, which is normal. Cool. Kind of got scared there for a bit, but it's all under control. Right, so now we have all this, we can probably get rid of some of these logs, but let's leave them in for now. Cool, so let's add something here. So for mmap, entries, get an entry, and let's log.debug, and let's go for any, yeah, sure, and do entry. Okay, let's see. Right, very cool, very cool. Okay, so now that we want to do this, we are just going to go back to our mmap entry definitions, and we are going to look for everything that's marked reclaimable, and we are just going to mark them as free. Right, so let's go ahead and do that, and actually let me do something like this. Yes, so if entry dot get type, do we have get type? Yes, we do, is equal to reclaimable. Rather, let's invert this, do continue. There we go. Otherwise, entry dot set type. Do we not have set type? Oh, so we. Hold on. Right. So I guess we could do something like entry. What's it? So boot info dot mmap entry dot create with entry dot get type. Rather get pointer entry dot get size and dot free. Yes. Okay. Let's go take a look at this. And actually, hold on, let me just put back the debug logs that we had before. Any something like this, and entry. And here we can just go ahead and do after any entry. Okay. What's that? Cannot assign to constant. Why is it a constant though? Sure. Okay, so let's see. So we have a ton of befores. And this one went from a reclaimable, which is 7, to a 5, which is 3. Okay. But hold on. Is this not a reclaimable one? 7. I'm gonna have to do some pointer 0x hex there. Size would be this, bytes, and type would be any. Right, so entry dot get pointer, entry dot get size, and entry dot get type. Okay, can do this. And let's just do this here and do after. Okay. Hopefully this works fine. So, looking for reclaimable. Okay, so this one becomes free. And it's the only one we have. All addresses and sizes look correct. Yeah, sure. Actually, are the sizes in pages or in bytes? I always forget this. Yeah, sure. What are our sizes in there? So get memory map. Descriptor size. So it's in pages here. Physical start. But okay, so number of pages is basically number of pages, and okay, so it's in bytes. But we do have a problem then. How can we get something that has 8 bytes if it's... I guess we can, if this is... So this is a multiple of a page size. I can see that. Let's check this one. Let's check if this is a multiple of a page size. So 496, 12. Yep. Okay, so we are all good. No problem there. Right, we can get rid of this. We can also get rid of this. It's all fine. Cool. So now we have reclaimed our pages. We have a problem since now we... let me rerun this. Cool. So... so where is our reclaimable? There we go. So this one here has become free. And right next to it, we do have another free region here. But we did not merge the two, so it's something we need to keep in mind while working on this. So for this step here, we just reclaimed all the freeable memory. And actually, I would like to do something like this, probably. Yes. So I think this is a good point to break this episode here. Go touch some grass or something. But we've laid out some groundwork for the work that needs to be done. We've solved all the blocking issues and we just need to basically go on with our plan. So that's pretty much it for this one. Hope I see you on the next one. Fucking hell.